In this video, we're going to talk about calorimetry. And this is a way that we can measure the heats involved in chemical and physical processes in the laboratory. So when discussing chemical reactions and thermodynamics, we typically divide the universe into two parts, right? So we take everything and divide it into two categories. We either have the system, and so the system is the part of the universe that we're focusing on. And generally for a chemist, this is the chemical reaction that we're studying. And then the surroundings is everything else. So we have, right, everything in existence, and we divide that into the system, which is generally a chemical reaction, and then the surroundings, which is everything else. And so what we look at is how is energy exchanged between the system and the surroundings. And we know the two ways that energy can be transferred is through heat or work. And because of the law of conservation of energy, energy can't be created or destroyed. Any energy that's gained by the surroundings must have been lost by the system. Or any energy lost by the surroundings must have been gained by the system. And so if we can determine what happens in the surroundings, then we know the opposite must have happened in the system. So for example, if we find that surroundings absorbed 50 kilojoules of energy, then those 50 kilojoules must have been lost by the system. And the system is our chemical reaction generally. So a calorimeter is a device that's used to measure the amount of heat involved in a chemical or physical process. And a lot of the chemical reactions that we're interested in take place in solution. And so the diagram on the right is a schematic of a very simple calorimeter. So we have some polystyrene cups, right? These are just coffee cups that you might buy in a store. And we can get more fancy with the insulation, but this actually serves as a very good rudimentary calorimeter. So we have a thermometer to measure temperature changes. We have a stir bar to help us stir the solution. And so what we would do is we would measure the temperature of our reagents before the reaction, then dump them into this calorimeter and put the lid on, and then see how does the temperature change over the course of the reaction. And the change in temperature that we're measuring of the solution can tell us about the heat given off or absorbed by the reaction. So remember that when we have solutions, right, we have the solvent, the solute, and then the solution overall, right? And so the solute, those are generally the things that are going to be involved in the chemical reaction. And in terms of the amount of mass or the amount of matter that they make up of the overall solution, that's relatively small. And so the solvent makes up the majority of the mass. And so the total mass of the solution, or what's happening to the solution and the temperature changes of the solution, are really our surroundings. Whereas the things that are actually reacting are the system. And so when we measure temperature changes of the solution, we're actually measuring the temperature changes of the surroundings. And so if the temperature of our solution goes up, that means the surroundings absorbed energy and the system, the chemical reaction, gave off energy. And so that would be an exothermic process. Whereas if the temperature of the solution goes down, right, the surroundings lost energy. So that means the system must have gained energy. And so that would be an example of an endothermic reaction. So when we measure the temperature of the solution, we're actually measuring the changes that are happening to the surroundings. And so the system is the opposite of that. If the surroundings, if the water, our solution increases in temperature, that means it was an exothermic reaction, and our reaction lost heat. If the temperature goes down, that means our solution, the surroundings, lost energy, and so the system, the reaction, must have gained energy. So that would be an example of an endothermic reaction. So this is a schematic of a commercial calorimeter, something that we might pay hundreds or thousands of dollars for. But basically it works exactly the same way as using polystyrene cups. We just have, better sources of insulation, maybe more precise thermometers. But the same thing holds true. We have an insulated container. We have a reaction vessel where we mix our solutions and the reaction occurs, and maybe we have a more precise thermometer or slightly better insulation, but the idea works exactly the same way as the coffee cup calorimeter that we often use in general chemistry experiments. All right, so this is really just a reiteration of what we kind of talked about before. So our solution is the surroundings, and the system is the chemical reaction, right? And so whatever happens to the solution in terms of absorbing or giving off heat, the opposite is true for the system or the chemical reaction. So in an exothermic process, we know that the Q for the system is going to be negative, right? And so the system is going to be losing energy. Let's use a better color for that, right? And then that means that the Q for the surroundings, the Q of the solution that we're measuring, is going to be the opposite of that. So if the system is losing heat, then the surroundings is gaining heat. And so Q for the surroundings is going to be positive. And so if the solution is absorbing heat, then the temperature is going to increase. And so the delta T for the solution is going to be positive, right? The temperature of the solution is going to increase. For an endothermic process, we know that Q for the system is positive. That means Q for the surroundings, the solution that we're measuring, is going to be negative. And so the temperature of the solution is going to decrease. And so delta T for the solution is going to be negative. Alright, so I want to finish this video up with an example of what a typical calorimetry problem might look like. So in this case, we're told that we have 50 milliliters of silver nitrate. We're combining that with 50 milliliters of hydrochloric acid, and we're given the concentrations of each solution. And we're told that the temperature changes from 23.40 to 24.21. And we want to calculate the heat of the reaction. Now, for relatively dilute solutions, as we have here, we can generally make the assumption that the density of the solution is basically the same as the density of water. And so we're going to assume that the density of each solution is the same as that of water. It's 1 gram per milliliter. And we're also going to assume that the specific heat of each solution is also the same as water. And that's generally an okay assumption to make when we have, relatively dilute solutions. So the reaction that we have going on here, we don't actually really even need to know this to do the problem, right? But we have silver nitrate plus hydrochloric acid. And so if we were going to predict the products, I need to know the ions that I have, right? So I have silver is +1, I have NO3 minus, and H plus, and Cl minus. And so our products are going to be AgCl and HNO3. And so if we go to our solubility rules, nitrates are soluble, so HNO3 is going to be aqueous. And most chlorides are soluble, but one of the exceptions is when it's paired with silver. And so this is actually a precipitation reaction. So the AgCl is going to be solid. And so what we're taking advantage of here is that we know that the Q of the solution, that's the surroundings, is going to be equal, but the opposite sign of the Q of the reaction, which is the system. And they want us to calculate the Q of the reaction. Well, to do that, we know the temperature change of the solution. We know the mass of the solution. We know the specific heat of the solution. So we'll calculate Q for the solution, and then the Q for the reaction is just going to be the opposite sign. And so for the Q solution, right, we're going to use Q is equal to MC delta T. And the mass of our solution, when we mix these guys together, is going to be 50 milliliters plus 50 milliliters, right? And we're assuming that each solution has the density of water. So this is 50, if the density of water is 1, then if we have 50 milliliters, we have 50 grams of each one. So our total mass is 100 grams. Delta T is going to be the final temperature minus the initial temperature. And so we have 24.21 minus 23.40. So delta T is 0.81 degrees Celsius. So we now have the mass, we have the heat capacity, we have delta T, so we can calculate the Q for the solution. Right, so the degrees Celsius cancel, the grams cancel, and so we'll be left with our heat in joules, which is good. That's the units that heat should have. So the Q for the solution, I have 4 sig figs, 4 sig figs, and 2 sig figs. So my final answer should have 2 sig figs. So I get 340 joules. And then we're going to use, right, this is the solution, this is the surroundings. So the Q for the reaction is going to be the opposite of that. And so the Q of the reaction is going to be negative 340 joules. Right? The reaction gave off heat. This caused the temperature of our solution to increase. And so it makes sense that this is going to be negative because this was clearly an exothermic process.